video looks at some attributes of polynomial functions, 14.2. So we want to be able to sketch the graph of cubic functions, identify what we call the end behavior of polynomial functions, and define some basic polynomial vocabulary, or at least review that basic vocabulary. Okay, let's begin looking at some just basic terms for vocabulary that we've probably seen before, but just to make sure, before we get in further deeper into polynomials, we have to all have a common language here. Coefficient, remember, is the number next to the variable. So in this first box over here, for the term 4x to the fifth, the coefficient is a 4. It's a fifth degree because it has a 5 for an exponent. The second line here is a third degree, or cubic, 12x to the third, and our coefficient is 12. Here our degree is the second degree, and our coefficient is hidden. It's a 1. And here it's also hidden. It's a -1 for the coefficient, and this is also a hidden exponent of a 1. So if I draw that a little bit better there, this would be -1x to the first. Okay, so our degree is first power. So linear, our degree is 1. Okay, and the constant term would be a number, and we'll look at some examples in just a second on that. So constant terms are just numbers because they were always constant, like 4 is always 4, 8 is always 8, so forth. Okay, our next piece we're going to look at here is the degree of a polynomial. We just talked about that. You have to be careful to make sure it's in order, in standard form. That means the highest exponent first. In this first case here, we have highest exponent in the whole string for the polynomial is a 2, so the degree of the polynomial is a 2, and our constant term is the number on the end, so our constant term is a 7. For this next one, it's pretty easy to see our highest exponent is a 3, so the degree is 3, and our constant term is -3. Make sure you keep the sign with it. Now this next example, it's out of standard form, so we have to look at the highest exponent involved, and it's going to be a 2, so our degree is a 2, and our constant term is the number 36. Okay, so let's kind of put all that together here. It says here that the standard form of a polynomial is a polynomial whose terms are written in descending order of degree. So as we can tell here, this is already in standard form. The leading coefficient, it's the coefficient, the polynomial's leading term when the polynomial is written in standard form. So basically the leading coefficient, so that's going to be this piece right here. If we highlight that, leading coefficient in this case is a 7. That is our leading coefficient. I'm going to abbreviate there. Leading coefficient is a 7 because it's next to the highest exponent term. Okay, now we're going to have a degree of 5 here. Degree of 5, that's going to be this piece here. Okay, let's pick up a couple other pieces here. This right here, this -3, is our constant term, and that's equal to -3. And then our last piece that I want to get across is what are all these 3 arrows at the bottom? What am I trying to indicate there? These 3 arrows, we call these terms of the polynomial. And terms are separated by pluses and minuses. So this has 3 terms. Okay, this slide just reviews the names of polynomials. So we have monomial is going to have 1 term to it. So there's a monomial, and a monomial. Okay, this just has 1 term. Notice there's no pluses or minuses. Here binomials have 2 terms. That's 2 examples of binomials. And then of course trinomials, just like tricycles, have 3 wheels. Trinomials have 3 terms like that. And then anything bigger than that, there are names for them, but we typically just call them polynomials. So be comfortable with doing that. Again, if you want to look up the names, you're welcome to do that. Okay, this next piece, I just want to talk about sketching polynomials and what the different pieces are as we go to sketch them. You'll get more comfortable once you get the hang of graphing polynomials. Like this is a cubic function. I know this because my degree is 3. It's the highest exponent there. It's a cubic function. So when I go to graph this, I want to be able to see the whole graph. And so you'll get comfortable realizing that a cubic function kind of does this, or it could start on the other side, but it always has one little twist in it like that. So if your window isn't set right, sometimes you won't see the whole cubic function. So like if I zoomed in on this little box right here, my graph would look like this. But that looks more like a quadratic. It's because my window is not big enough. So I need to set my window. Notice this one, the y-scale goes all the way up to 30,000 and the x goes to 40. So if you have a 10 by 10 window, in fact, you're not going to see very much at all. You're going to be way down in there. In fact, smaller than that. So you won't see a good picture of it. So the first thing is recognizing how to set a correct window. And that just comes with experience and trying to graph some. And also be able to recognize what a cubic function looks like so that you actually know what you're looking for there. A couple of pieces that we already talked about in a previous video were relative maximums. There's a relative max right there. It's that point. And then relative minimums. Okay, we've got a relative minimum right there. Okay, so, and those are just bottoms of the hills are relative minimums. Think about bottom of a hill. And then tops of hills are relative maximums. Again, as I discussed in the last video, cubic functions just graphed on their own without context or without a word problem, they keep going on forever. So this thing keeps going that way, just like these arrows indicate. And so there is no absolute max for this one. Absolute max does not exist for this one because it keeps going forever. But we can have relative maximums, and again, that's going to be the top of a hill somewhere. Okay, and for this case, this had to do with a volume problem, and it tells you that the relative maximum is right there. So that would be the maximum volume you could get out of the piece that you were trying to do there. And then lastly, you can talk about x and y intercepts. Those are going to be where they cross the x and y axis. Okay, the next piece we're going to bring in is what we call end behavior. It's going to be a little confusing, just like anything else in mathematics. The notation is the biggest barrier. So I just want to go through a visual here about what these expressions mean right here, like this. Okay, the way we say this is we say as x approaches infinity. So this piece right here is said as x approaches infinity. Okay, we can kind of see that there. So that's what that arrow means, in case you see that. Now, what I want to do is, I think the notation is a little bit confusing just stand alone. So I want to go over a couple things here. I want you to think, when you see this one right here, I want you to think I'm looking to the right on the graph. Okay, because we're saying as x approaches infinity. So as we look all the way out here to the right, what's happening with the graph? We want to determine at the very end of it what happens. Okay, over here on the left, this one says as x approaches negative infinity. Now the first thing I'm going to do is show you how I like to introduce it to students. I don't like the way the arrow's pointing this way because that kind of implies that you're looking right. So a lot of times when I first introduce this to students, I have them write it like this. And I think that's a little bit helpful. So as x approaches negative infinity, going that way. Let me write that a little bit better there. Okay, so as x approaches negative infinity. So again, there's our arrow as x approaches negative infinity, going that way. So think about it as looking left. Okay, so when you see that statement, as x approaches negative infinity, you're thinking, I'm looking left. What's going to happen on the graph? Okay, the next piece would be looking up. As x approaches positive infinity would be upwards, looking upwards. And then our last piece down here is down. As y, I'm sorry, did I say that as x? This is as y approaches positive infinity. And this one is y approaches negative infinity is looking down. So that's the notation on those things. Okay, so let's put that to use. This example here, I've got a cubic function, which we've talked about many times here in the first two sections. This one, just want to make sure we know that we have arrows that happen here. So this cubic function keeps going up and down in those directions. So let's remember our directions that we laid out here. And so the problem will say something like this. It says, that is, you look to see what happens to y as x approaches negative infinity and positive infinity. So it'll say, as x approaches infinity, then we need to answer the question what y does. Well, if we look all the way to the right here, what's happening to the end behavior of the graph? Well, we can see that it's going down, right, on the right side. So we answer this question by saying y approaches negative infinity, like that. Okay. Now let's look left. And again, if it helps you, kind of think about it, written this way. As x approaches negative infinity, what's happening to y? And as we see here, as we look left, the graph actually goes up. So we want to say as x approaches negative infinity, y approaches positive infinity. And we typically won't write the positive, but I put it there just for now. Okay, so we've answered the question. Let me highlight the answers. The answer is here, right here. Okay, so the answer for this piece is given by this piece here. So the answer is, I have a little trouble with my pens there, sorry. So as x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, y approaches negative infinity. Let's look at another example to make more sense as we go. Okay, here's another one. This one's a quadratic. It's a U-shaped graph. And so as x approaches positive infinity over here, we're going to be looking right on the graph, and we can see that it goes upwards. So as x approaches positive infinity, y approaches positive infinity. Okay, and we look at this piece over here. As x approaches negative infinity, so as we look left, the graph also goes up. So y approaches positive infinity. Okay, so quadratics that open upwards have this end behavior. Here's another example. This is another quadratic, but it's upside down from the other one. And again, so we're going to look at our end behavior. We're going to say, as we look to the right, what's happening on the graph? Well, it's going down, isn't it? So we say as x approaches positive infinity, y approaches negative infinity. As we look on the other side, we can see it has the same end behavior on both sides. So as we look left, what happens to the graph? It also goes down on that side. So y approaches negative infinity. Okay, now let's see if we can come up with some generalizations that happen. Okay, when we have what we call even degree functions, so don't confuse that with even functions. Even degree polynomials, and these are all even degrees here and even degrees. That means the highest exponent is an even number. Again, do not confuse that with even functions. That's a very specific definition that we'll get to later. Okay, so as we look at these examples up here, we're going to talk about the end behavior. So as we look right, so as x approaches positive infinity, so as we look this direction, what happens to y? Well, we can see all the graphs, all three of those equations, the y goes upwards. So y approaches positive infinity. Okay, now let's look at the left side and see what happens. Okay, so as x approaches negative infinity, so remember this is looking left, what happens? Well, it also goes up on that side there as well. So we say y approaches positive infinity. Okay, same thing down here. Now if we put a negative in front of our even degree polynomials, it'll flip upside down as we can see here. So again, we're going to go through here and look to the right. As we look to the right, okay, so as x approaches positive infinity, as we look to the right, it looks like the graph goes down. So we say y approaches negative infinity. And as we look to the left, it has the same end behavior. And this will happen for all polynomials of even degree. They will have the same end behavior on both sides because they make either a U shape or a U shape with kind of a twist in it. So both of these go to negative infinity. Okay, now let's look at some, this will be our last slide here. We're going to look at some odd degree polynomials. Again, don't confuse that with odd functions. That's quite a different definition. So odd degree polynomials, and what I'm talking about here are these cases where we have cubic, fifth power, ninth power, and even here where we flip the sign. They're all odd degrees because the highest exponent is odd. So as we look at the end behavior, again, let's go over our notation. So as x approaches positive infinity, so as we look to the right here on this graph, what happens to the y's? Well, they go up forever, so we say y approaches infinity. Okay, as we look to the left, so this time, let's see, as x approaches negative infinity, and again, remember that's left, we're looking to the left, what happens to the y's? Well, we can see they go down forever. So we say y approaches negative infinity. Okay, next piece we're going to look at here is where we put a negative out front of the equation. That's going to flip our end behavior, as you can see from the graphs. So we'll go back through the beginning here. We'll say as x approaches positive infinity, what does y do? Well, let's look to the right. So as we look to the right here, it looks like they all go downwards. So we say y approaches negative infinity. Now let's handle the other case as x approaches negative infinity. So looking to the left, what happens to the grass? Well, it goes up forever. So we say y approaches positive infinity. Okay, so that takes care of basically almost everything you'll run into as far as end behavior goes. Notice in this case, our end behavior is split when we have odd degree polynomials. That concludes our attributes of polynomials. Hopefully that helped. Have a great day.